Hi everybody, welcome back to the Feynman technique. Today we're going to be evaluating this integral. This is yet another integral that I got off the channel Michael Penn. He uploaded this one recently, within the last week I think, so I'm going to link to that video in the description. This is a very classic example of how to use the Feynman technique. It's just, you reparameterize it, you take a derivative with respect to the new parameter. That makes the integral much nicer to evaluate. You anti-differentiate it with respect to the new parameter, and then you can figure it out from there. So let's see, where do we start, or what's the correct reparameterization to make in this case? The correct thing to do to perform Feynman integration is to replace that 3 with a t, and then call this a function of t, which it would be. And then we'll just say that our I is equal to our new function of t evaluated at the point 3. Because if you plugged in 3, you just have what we had originally. Okay, so now this helps us because now we can use the Leibniz rule for differentiation under the integral sign to take a derivative of our function of t with respect to t directly by just taking a partial derivative with respect to t of the integrand and leaving the rest alone. So our f of t is going to look like, well, hold on, we already have f of t. So what would our f prime of t look like? All right, f prime of t would be equal to the integral from 0 to infinity of the derivative with respect to t of this thing. So let's see, what would that be? Well, this 1 over the square root of 16 plus x squared is not dependent on t, so we'll ignore it for now. But we will have the derivative with respect to t of arctangent of t over the square root of 16 plus x squared. That would give us 1 over t squared over 16 plus x squared, all of that plus 1, and then times 1 over the square root of 16 plus x squared, and then again times 1 over the square root of 16 plus x squared. So I believe it would just be this. We would just have x squared plus t squared plus 16 dx. And that's not a hard integral to evaluate if you remember that integrals in this form that's equal to pi over 2a. So this is the same form as that, just with our a squared being equal to t squared plus 16. So in this case, our a would be the square root of t squared plus 16. So this whole integral evaluates to pi over 2 times 1 over a, which is the square root of t squared plus 16. So there's our f prime of t. We've reduced f prime of t to nothing but this, something in a non-integral form. So we can get f of t by anti-differentiating this with respect to t. So f of t is going to be equal to pi over 2 times the indefinite integral of 1 over the square root of t squared plus 16 dt. Okay, now I don't remember. This is an integral that I believe you're a lot of times required to memorize. I don't remember what that evaluates to off the top of my head, so let's go over here and make a triangle, and we'll just figure it out. All right, we'll make the angle theta, and it would just be convenient to make this thing the hypotenuse of that triangle. T squared plus 16. And then we could have t and 4. Right, because that's a valid triangle. This squared plus this squared is equal to this squared. So that's the correct setup. All right, so we'll have tangent theta is equal to t over 4. I'll just put that 4 in front of the tangent theta. All right, so that means 4 secant squared theta d theta is equal to dt. Okay. So now that's going to give us pi over 2 times the indefinite integral. Well, let's see. What's 1 over the square root of t squared plus 16? Well, 4 over the square root of t squared plus 16 is equal to this side over this side, which is the cosine of theta. But we want 1 over the square root of 16 plus t squared. So we just divide that by 4. So that is going to be this right here, this part is going to be equal to cosine theta over 4. So we'll put over 4 and then cosine theta. All right, now we have our dt. Our dt is equal to 4 secant squared theta d theta. That 4 will cancel with this 4. Secant squared theta, one of those secants will cancel with that cosine to just give us secant theta d theta. So that's going to be equal to pi over 2 times the natural log of secant theta plus tangent theta. All right, but we want our f of t described in terms of t, so we need to resubstitute using our substitution over there. So that's going to give us f of t being equal to pi over 2 times the natural log of, well, let's see, secant theta. Secant is this over this, so that's going to be the square root of t squared plus 16 over 4, right? That is secant theta, and then tangent theta, which is t over 4. Okay, so if we evaluate this function at the point 3, we will have the answer to our original integral. So that means I is equal to pi over 2 times the natural log of, okay, let's see, what's this part going to give us? 3 squared plus 16 is 25. Square rooted is 5, so we have 5 over 4. And then, let's see, plus 3 over 4. So that's 8 over 4. So that's just natural log 2. So that is the answer. Pi over 2 times the natural log of 2. And there you go. Very, very classic example of how to use Feynman integration to solve a tricky integral, and I hope you enjoyed that.